continuing on our discussion of last time, we were talking about the different cardinalities of sets. So now we want to define countable and uncountable sets. So just kind of to recap what we saw in section 14.1, if two sets have the same cardinality, we could say that two sets have the same cardinality if there's a bijection between them. So I say that the cardinality of A equals the cardinality of B if there exists some bijective function f from A to B. We saw that the cardinality of the natural numbers is the same as the cardinality of the integers. And we saw that the cardinality of the natural numbers is not the same as the cardinality of the real numbers. So there's going to be a lot of sets that do have the same cardinality as the natural numbers. So we're going to give those sets a special name, and those are going to be our countable sets. So let's talk about that on the next slide. So if I have a set, I'm going to say that that set is countably infinite if it has the same cardinality as the natural numbers. So the natural numbers have the same cardinality as themselves, so they're countably infinite. We saw that the integers are countably infinite. The even integers are going to be countably infinite. The odd integers are countably infinite. Right? So that's going to be true if there's that bijection between the set and the natural numbers. That gives us that they have the same cardinality. It's countable if it's either finite or countably infinite. And then it's going to be uncountable if it's infinite and it does not have the same cardinality as the natural numbers. So there's no bijection. So let's just going to go through and think about what we know about the sets below. So this first set is finite. We've talked about that before. And these two are infinite. Now, these new terms, countably infinite means it has the same cardinality as the natural numbers. And then it's countable if it's either finite or countably infinite. So both of those two are countable. And then if it's infinite, it doesn't have the same cardinality of the natural numbers. Choose one more color here. That is going to be uncountable. So I have my finite and infinite sets, but that's different than saying countable or uncountable. So the integers and the natural numbers are countably infinite, where the real numbers are uncountable. We want to talk a lot about these countably infinite sets. And so we want to think about what their cardinality is, right? But that's not a number. It's not a finite number. But I don't want to just say it's infinity because it's a different infinity than the cardinality of the real numbers. So because this is a special concept for us, we want to give it a name. So the cardinality of those natural numbers, we denote with this symbol here, which is aleph naught. So let me write it down. Oops. This is my aleph, the first letter in the Hebrew alphabet, and then it's just a naught, the little subscript of 0. So I use aleph naught to represent the cardinality of those natural numbers. So to get this symbol in LaTeX, we're just going to do / aleph, and then you can do _0 to give you the naught there. So that's the cardinality of those natural numbers. So what's special about these countably infinite sets? So remember, if I have a countably infinite set, by definition, the cardinality of that set A is the same as the cardinality of the natural numbers, which means there exists some bijection from the natural numbers to A. And now, like we tried to do in our proof that the real numbers were uncountable, if I have this bijection, I can think about what f of 1 is, and f of 2, and f of 3, and so forth. And if I take that entire collection, that will give me all of A. So what we usually do is we think of f of 1, so the image under 1, under this bijection, as our a sub 1, f sub 2 is our a sub 2, this is our a sub 3. So if a is countable, then I can write it out as sub a sub 1, a sub 2, a sub 3, so forth, in a way where I get every single one of the elements of A. So there is some way to enumerate or list in some order all the elements of A. So if I have this countable set, then I can actually enumerate out all of those elements. And that's actually an if and only if. So we have this theorem that tells us that a set is countable if and only if there's a way to list out all of the elements in that. So let's go ahead and write that out. So a set A is countable if and only if, let's say countably infinite, a set A is countably infinite, so it has the same cardinality as the natural numbers. If and only if its elements can be arranged in an infinite list. A1, A2, all the way up. Right, and I don't stop because it's an infinite list. So whenever we're trying to prove that something is countably infinite, if we can think of a way that we can list out all of the terms in a way where we're guaranteed to get every single one of them exactly once, then we know that that set is countably infinite. So that's helpful for us. And in fact, this is what we're going to use to help us consider whether or not the set of rational numbers, Q, we want to think about whether or not that's rational, or sorry, that's countable. So think for yourself, is there a way that I can list out all of those rational numbers in a way where I'm not going to miss any of them? So again, that question that we want to ask ourselves is Q countable? Can we list out the elements of Q in a way that we get all of the elements? So let's think about what those elements of Q look like. So this is going to be the set of M over N, where M and N are in Z. Wrote Z there. Right, N not equal to 0. So how can I think about listing out all of my rational numbers? One way we might do it is to think about the numerators. So I can have 1 as a numerator, or 2, or 3, or 4. Maybe we should plug in the negative numerators as well, just so we're not missing anything. And then I could have my denominators. 1, 2, 3, 4, 5, and so forth. And now I can just sort of pair those up. So this gives me 1 over 1, negative 1 over 1, 2 over 1, negative 2 over 1, 3 over 1, negative 3 over 1, 4 over 1, and so forth. And then I can get 1 over 2, 1 over 3, 1 over 4, 1 over 5. So I can just go ahead and plug these in to get all of my rational numbers. So I want you to think for yourself, as we do this, are we definitely going to get all of the rational numbers here? Or are we going to run into some issues? So let me go ahead and just plug in a few more of these as we go. Okay, so hopefully you're starting to think about whether or not I'm going to get all of the rational numbers. Every rational number is going to have some positive or negative integer on the top. I guess I should throw in a 0 here. And it could be represented with a positive integer on the bottom. So I certainly, if I fill in this whole square, will get everything. But then I need some ways to list them all out. So if I start trying to list out all of my rational numbers by going all the way along this top row until I reach the end, then I'm never going to reach the end. It's an infinite list, which means I'll never get down to the next row. So that's not going to be a good way to do it. So instead, we have to sort of think of a creative way to travel through this list of all of these rational numbers to ensure that we get all of them. So we want to do something like this snake. So maybe I first go to here, and then down and up and over, and down and up and over, and down and up and over, and so forth. Something like that. And now I can guarantee that I've hit every single one of these rational numbers in some finite amount of time. So if you give me some number really far out, I can tell you how many steps it will take to get there. Now, there's a few more issues that you might have noticed. For example, I'm not going to get a bijection if I do this. Right? The number 2 over 2 is the same as the number 1 over 1. Or maybe the number negative 2 over 2 is the same as the number negative 1 over 1. So we have to be a little bit more careful. I could just say that I'm going to skip any of the numbers that I have already included. So anything that's not in lowest terms, when I'm doing my enumeration, I'm just going to skip that number. Or when you're writing these out, maybe I'm just going to not even include those denominators if I already have that counted. So we'll look at some examples of different ways that we can do this on the next slide. But the idea is we're going to use this sort of snake argument to move through our rational numbers in a way that ensures we get them all. And because we can enumerate those out, it turns out that Q is countable. So I do get that, yes, fill that in, Q is countable there. So let's look at some of these different ways of dealing with this one-to-one issue on the next slide. Okay, so on the left is the book's solution to this. So each of these columns is represented by the different positive and negative integers. So I've got the 1 column, the negative 1 column, the 2, the negative 2, the 3, and so forth. And then in the denominator, I'm just going to think of all of the different denominators that I can have to go with that. So for 1, I can have any number go all under 1. So I'm just going to list every single one of those. And the same thing is true for negative 1. For 2, I want this to be in lowest terms. So I'm not going to include any even numbers in my denominator. So I'm only going to have the odd ones. 1, 3, 5, 7, 9, 11, 13, and so forth. And the same is true for negative 2. For 3, I don't want any multiples of 3 in my denominator. So I'm just going to have all of the numbers except multiples of 3. So I'm skipping 3, I'm skipping 6, I'm skipping 9 as my denominators there. And the same thing is true for negative 3. And then we go through. Here for 4, I don't want to have anything in common at all. So I also can't have any 2's in common. Right? I want the GCD of the denominator and the numerator to equal 1. So I'm just going to list all the possible ones there. And then again, we just have to come up with some snake pattern to allow ourselves to go through and enumerate every single one of those. And again, every single one of my rational numbers will be listed here, and I will get to it in some finite amount of time. Therefore, that's going to be an enumeration. So therefore, we know that this set is countably infinite. The other picture we have here is more what we were describing, where we have the numerators. So here they actually put the numerators going down the row. So that's 1, 2, 3, 4 as my numerators. And then across the columns were the denominators. 1, 2, 3, 4, 5, and so forth. And they did this typical snake pattern. And the ones they highlighted in red, which I'll highlight again in purple, those are just the ones they skipped because they weren't in lowest terms, so they were already listed in a different spot. So we just skip over anything that's not going to be in lowest terms, and then we sneak through. So the order doesn't matter that we get them, right? I'm not getting them in numerical order or anything. I just need to make sure I have some way to ensure that I'm going to get to each of these numbers in finite time. So both of these are different ways that we can think about this enumeration of those rational numbers. And because I can list them out in a list that gets everything, that means that the cardinality of those rationals is equal to the cardinality of the natural numbers. So there's the same number of natural numbers and rationals, but there's more real numbers than natural numbers, which means there's more real numbers than rationals as well. Okay, so one final theorem here. We have that if A and B are countably infinite, so is their Cartesian product. So I want you to think about how you can show this, and think about it in terms of the proof of the fact that the rational numbers are countably infinite.